So, good afternoon, everybody. It's a great pleasure to have here our colleague Maria Pia and Mauro from Rome. So, for our seminar sessions. Maria Pia, after completing her PhD in physics with a research conducted at the Nicolas Copernicus Center in Warsaw, built an international career at prestigious institutions, including the University of British Columbia and Aarhus University, right? Where she specialized in stellar oscillations. Currently, she serves as a researcher at the INAF Istituto di Astrofisica e Planetologia Spaziali. Her scientific research focuses on the use of helio and asteroseismology techniques for stellar physics, as well as developing synergic tools to characterize solar-like stars and investigate the habitability conditions of exoplanets. So, Maria, you will have 45 minutes, and I will warn you 5 minutes in advance, okay?
Thank you very much. Let me thank, first of all, let me thank everybody and primarily the organizer for inviting me to be here. And my primary host, which is Santi Cassisi, probably is not even online. He is actually the person that put my name in the hat. So I'm here thanks to him. And actually, I'm very happy to see so many people because this in my institute doesn't happen so often. So today I have the chance to explain and to present what is astroseismology. So I will give you a short introduction to this methodology. And in particular, I will point out the importance of these techniques for several fields of astrophysics. Of course, mainly for stellar physics, but not only. There are also implications for the knowledge of our galaxy in exoplanetary science and also nuclear physics. It's something on which I would like to get your attention, and perhaps you can even suggest where I can help you to infer better. As I said, I will give you a first introduction, very short. So astroseismology is a word that you can find also in the dictionary, and is the study of the interior of the stars by observation and analysis of oscillation at their surface. So this is the real definition that you can find everywhere. The point is, what are these oscillations, of course? What we have seen during the last decades has been a huge revolution in astrophysics, thanks to the data that have been provided by space photometry. So since the launch of the first photometry space mission, which is the Canadian MOST satellite, then after the Corot and then Kepler, and till to today, we still have the TESS flying. The main result is actually that variability can be observed. So this variation in luminosity and the movement of the surface can be seen everywhere. If we look at an HIR diagram like this, you see the different colors indicate different families of oscillating stars. But in particular, of course, I'm concentrated on this pink shaded region, which is the region of the solar-like stars. These are the stars which, like the sun, are characterized by a layer, an envelope with a turbulent convection. Mainly we identified these stars with a main sequence, post-main sequence, even giants, and a different spectral type like FGK. Small periods and an amplitude that is very, very small. We are speaking with about some centimeter per second. Very small difference also in luminosity, in intensity. Let's try to understand what is the difference, because I think that this is actually the problem, to try to understand what is the difference of these solar-like stars, why they are so important to respect of other stars. Because we have seen and studied always Cepheids, Lyra, we know the K mechanism, and also we have studied the exomechanism, the excitation of pulsation with one mode, and as well explained by Eddington, we know this cycle that excites and produce this oscillation. This is a different, solar-like stars is different. And to try to understand that, I have to go a little bit behind in time, starting with the sun, but I will go just quickly. In the period of the 70s, when some observation of the surface have been produced by these people, Ulrich, Lebaker, and Stein, and when they were observing this surface, they were seeing up and down variation in interpreted as Doppler effect, and this was at the beginning was attributed to granulation, supergranulation, not real movement of the entire of the global star. It was a little bit later, 75, that Dobner produced this kind of spectra. This is a power spectrum, and you see that the power of this oscillation is not just randomly distributed, but is very well distributed in frequencies and the horizontal wave number. The explanation of this can be understood in this kind of sketch. So what you observe on the surface are acoustic waves which interferes with each other, each mode with a particular frequencies, and is trapped between the photosphere and the layer in the inside, which depend only by the temperature. Let's say that a star like the sun is an instrument, a musical instrument, and can produce only some tone, some music, some mode that are only of this star, depending only on the size, the mass, the density of this instrument, like any other instrument, a musical instrument. So this is the best of this technique, because we know actually how to study acoustic waves. So the properties actually of the power spectrum is similar to a power spectrum of a violin, and the frequencies that you can observe are the similar of any other instrument, which means fundamental mode and all the other overtone, equispaced by what we call large frequencies, but it is exactly corresponding to the large frequencies in music, in any musical instrument. This is the typical asymptotic theory with which we describe the acoustic modes. So this large separation depends exactly by the dimension of the instrument and the mass. There is also a very small difference, which is called small separation. This is, in the case of musical instrument, it depends on the density of the string, for example. So it's mainly dependent on the features of the core. So tell us mainly what is the production and nuclear production in the core, and then it's related to the age. The type of oscillation that we can observe in the sun and stars similar to the sun are acoustic waves, but also gravity modes. So if this is the sun or a main sequence stars, so you see the frequency as a function of the radius inside. So we can distinguish two cavities, the acoustic cavity, where the acoustic waves can propagate, and the gravity cavity. This is just to tell you that from the theoretical point of view, we can observe, or we know that this kind of modes can be excited in the main sequence stars. But in the case of the Sun, for example, these modes have not been observed, let's say. But the theory predicted the existence, and actually we have been observed in other kind of stars. Today, the things are not so easy, so we know how to implement the modeling of the excitation of this mode. I will show you in a while, but actually there is an effort to understand the excitation of each of the family that I've been showing. So let's say that in trying to simplify, I tell you that the modes that we observe are only gravity modes and P modes, but in truth, we have all kinds of modes according to the condition of the typical stars. And there are some efforts like the rotation and the magnetic field that needs to be included in the modeling of the excitation mechanism. But I don't want to make things too difficult. And so the mechanism for the excitation of the acoustic pulsation, actually, as I said, is the turbulent convective motion. This is a very nice sketch that I found. So if we look only on the left part, we see that there are the cells, and they're moving up and down. They are moving energy and producing sound, giving energy to these waves, and generating acoustic waves. And here you see the movement. At the same time, we believe, so the model that has been built by these people, very well and well-defined model, is actually that the same convective motion damp this observation. So the point is that these waves, sorry. So the point is that the waves are standing waves, but they are stochastics. So when you observe a star, you don't see those frequencies, those modes all the time. It's like that someone is bumping a bell, and so the noise is staying there for a while, the music is staying there for a while, and then is damped. Again, the convective cells are taking energy from these waves. So this is the sketch of the excitation source, like a number that is bumping actually the bell. The acoustic cavity is the star, and then the same damping is here, like in this sketch, is the contrary of the hammer. In the case of the gravity modes, very interesting is this stochastic excitation of the gravity mode through the penetrative convection. It's actually, again, the convective motion that is exciting, penetrating in the radiative zone, can excite again the gravity modes. The behavior of the gravity modes, this is P is the period, so it's very equispaced in period, not in frequencies like in the acoustic waves. So again, also in this case, if you observe the gravity modes, then you can study the interior of a star, and in very easy way you can distinguish the modes by period. Okay, like for example in this spectra. After 30 years of data, we saw the solar satellites. Now we have thousands of modes for the case of the sun. These figures just to show you that the oscillation can be observed in two ways, which is radial velocity. These are the two instruments flying on Sol. So one was observing Doppler movement of the surface, so in velocity, and the other one is a photometric instrument, is Virgo. This is just to show you that the way in which the two instruments, the way in which we can observe the oscillation, give anyway hint of the spectrum of oscillation, but there is a very big difference here, which is actually due to noise and other feature. When we observe from the photometric point of view, you have a global spectrum, and here you have everything in. You have rotation, you have granulation, you have white noise, and also the noise due to the sunspot. So let's say that to observe oscillation, it's better to observe by velocity, spectroscopically, but we have a photometry. So we have to deal with this problem every time that we observe the oscillation of a star. So we have to extract the information from a global power spectrum. Asteroseismology, perhaps you know or not, has been a kind of a revolution for several points of view, for understanding that the star can be studied in deep. We now know, I don't know, that we have solved the problem of neutrino problems, the differential rotation inside. We know that the difference of our models, this is the difference in sound speed, is only few percent, and the only problem is just at the base of the convection zone. So it has been really a difference in the 90s to have asteroseismology to study the sun. But now the point of this talk is more, can we extend this method to other stars? This is the situation of the solar-like stars just a few decades before, so before the launch of the first space mission. As you can see, we have observed from some of the facilities from ground only few solar-like stars where we have identified some of the oscillation. I mean stars like Beta Hydri, Procyon, very bright, very well-known star. Things have started to change with Corot, which already identified several giants. And then Kepler, of course, changed. Now we know a lot of stars. We are speaking about 120,000 dwarfs and 37,000 subgiants. With these numbers, can you understand already that things have changed to understand how things can be done? So we have a very interesting sample of stars on which to prove our stellar model and the stellar physics in general. The red giant in particular, before the 2003, well, this is most, but even before Corot, let's say, we didn't know that solar-like stars could be observed in the red giant, but now we have several red giant, and it has been actually the great hit of Kepler. What is most important of the red giant is that as the star evolve and the core shrink, what happens is that the G-mode cavity became even smaller. In this situation, gravity mode we can have a frequency is very similar to the one of the P mode. This mode can interact and give rise to mixed mode. The mixed mode is very interesting. It's a mode with waves with this behavior. So they can be observed at the surface, but they give information of the inside. So more waves, more nodes you see, it means more information of that region, more we know of that deep layers. This is the reason why this red giant have been very interesting. First, because now we know that actually the gravity modes exist really, and secondly, because we can infer the core that was not possible to infer. The basic tools of asteroseismology are just taken from the spectra, the oscillation spectra. As I said, we have this excess of power due to the oscillation. The shape of the spectrum is a typical like a bell, where you can distinguish mode with different harmonic degree. The separation is the large separation, the separation of each mode. And then there is another important feature, which is the main frequencies, nu max. And this is related, so the frequencies of maximum power of oscillation is related to the acoustic frequencies, which means the maximum frequencies of this musical instrument, above which we cannot have other music, other sound. So large separation and nu max are the two features that usually you can use. These are very simple way, in the case of the sun, are related to the mass and the radius. So we can use these tools in a very easy way. Of course, if you want to go deeper and to know better what's going on in the star, then you have to use each mode, each oscillation, which give you information in the inside. So what we use for large sample, like looking at all the red giant or clusters, we use this Kelvin law, which very easily related mass and radius to larger separation and nu max. And if we put in a kind of diagram, you see that there is a very nice relation. So from the sun, you see that a decrease of the larger separation and a decrease of the nu max up to the red supergiants. So the delta nu decrease linearly and nu max decrease as the star evolves. So we expect this kind of behavior. As I said, if we want to know better what's going on in this star, so not only the parameters, but study the properties, the physical properties, internal properties of the star, then what we do is to use stellar models that need to reproduce this oscillation. But also we use all the ingredients. So model that we produce have to reproduce the oscillation, but also luminosity, spectroscopy, also the distance, and then we get the luminosity to produce better models. Of course, better is the model, better is the properties that you can infer. And then there are several pipelines online that you can use. You can even produce your own pipeline to fit all the frequencies, large separation, effective temperature, gravity, all the information that you have of these stars to try to find the best model. So these are the tools that actually we use. There is still one other problem. As I said, the oscillation are used actually to prove that our understanding of the physics is not so good. And one of the main problems that we have is the surface of the star, because our models are not so good modeling several effects that are on the surface, which mean we assume adiabatic condition, and actually in the surface we don't have adiabatic condition. The equation of state is not so well known at the surface. Also, there is the model of the convection that many of you know. We are still relying on the mixing length, so it's not exactly what reproduce the observation. So this to tell you that our model, if we calculate the difference between theoretical frequencies and modeled frequency, you will see this difference. The difference up to 20 microhertz. And these are the modes, because you see that these are at high frequencies. These are the modes that are trapped on the surface and give us information. So what we do, something that is not exactly what we want to do, because you have to produce a model. So what we do is to try to parameterize this difference and adjust the frequencies that sound the upper layers. So there are several scaling homology laws that are used to adjust this surface effect. This is still something on which there is people that is working, like Rainer Trampedak and other people is working on producing 3D models for the surface. Still, it takes a lot of time and a lot of efforts to have something better. This is just, for example, an example for the case of Procyon A. Perhaps you know this guy is an F-type star, so which means that the envelope is very thin. The convective envelope is very thin. When we go, this is the way in which we compare the frequencies. The observed frequencies are the black, and the modeled are the green, and this orange is another model. So there are two models that actually can fit these 55 modes observed by embedding. And when we try to correct, actually, by using a scaling law taken by the sun, we discovered that they don't work. So for the F-type stars, we cannot use treatment as we do for the case of the sun, because if we try to compare, for example, the luminosity with a different prescription of the treatment of the surface effect, we see that the observed luminosity with the modeled is better in the case in which we don't use. This is just an example. So we should take care, when I say solar-like stars, actually, we should take care better of F-type stars, and we need to study this problem better. But if I want to go quickly to results, that for me, actually, I say the major result of perhaps just my result, because I don't want to give here all the result of asteroseismology, but perhaps you have heard already the use of asteroseismology for finding accurate and precise parameters. And this is very important at the moment in exoplanetary science, because they need very precise measurement, for example, of the radius with error less than 3%. Because any parameter of the planet is actually measured into consideration of the star. So they cannot measure the mass and the radius, and of course the age of the planet is the age of the star. But what has been more used for is for example, for the galactic archaeology. What I think that is more interesting for the testing of the physical interior. Today we were speaking about the use actually of seismology for equation of state and other features like the opacity, the nuclear reaction, internal rotation and angular momentum transport. What we know today it's thanks to the asteroseismology. And there are also other things like, for example, the depth of the convective zone, overshooting effect, transport, everything can be tested, let's say, with asteroseismology against any kind of model that you can think about. Even models, it has been tested even with model with dark matter. So to see if this is possible. We have a hint also about internal magnetic field. I will show you this, and the use of asteroseismology. Briefly, I will speak about star-planet interaction. So the main stellar parameters, as I said, we need very precise measurement, and it depends on what you have. So you can use scaling law, you can use stellar models and main asteroseismic parameters, or individual oscillation frequency, and then of course your measurement became more precise. What is interesting is to see if the asteroseismic mass can be compared with other kind of measurement. This, for example, by Peter Golm, it's very interesting because show you that what is the error of the measurement of the mass by asteroseismology in the case of binary stars. So we have the measurement of the mass which is independent by any model. And this is another use of comparing the measurement of the radius by asteroseismology. Here you see the measurement of seismology with different, so the orange and the red are with seismology, but with two different stellar model, and eclipsing binary, which is this, and the error 2-3%. And this is another, this was by Goldman, this is the blue is eclipsing binary, which is not too bad, it's not so far after all. So indicating how good we are in using these individual modes, or the scaling relation, which is the cross, by using instead the binaries. In the case of finding the parameters of an exoplanet by through the star, then we see that we can compare all the methods, asteroseismology, transit, and spectroscopy, and mainly the mass is actually the one that are better overlapping, and then the methods are really divergent. In particular for the density, if we use spectroscopy, for example. And here you see in the case in which you use Gaia astrometry. Again, this is the radius compared to the radius, the seismic radius compared with different methods. Of course, there are some disagreements. Still, we don't know which one is better. It can be an astrophysical bias, it can be a possible observational bias, but this is just to know how well we can go with the accuracy in the parameters. The other problem is the age. This is something that has been studied quite well, because there is an interest, for example, in galactic archaeology. Here I listed all the methods that we know, the lithium depletion, we have geochronology, different color magnetic diagram for using the cluster. What is the result by Lebretron and Goupil is actually that the error in the case we use seismic measurement becomes smaller. We can even use other cases. This is a case of a binary that we can use as a benchmark, a very well observed binary, but very interesting case. This HD 81809. in which the two stars are actually solar-like stars with a mass similar to the mass of the Sun. These are the observed, not the modeled. But what is very interesting here is that we have a binary with a completely different abundance pattern. So one is deficient in iron, the other one is solar-like. And here you see also the linear is very, very different. This means that if we use these parameters to model the stars, what we get is actually that we are not able to get the observed luminosity, although this of the luminosity can be even a different problem because we use it a different way to Tycho and Gaia inference of the luminosity. In the end, actually, this very strange binary indicates that the difference of the abundance can be only one, or one has been accreted some iron or some heavy elements from engulfment, for example, of a planet, or it has been captured from outside and is not a real binary, which is with the same age. So very interesting benchmark, but probably there are different different cases like this that need to be studied better. The age of the red giant, for the reason of the mixed model, is actually more precise than the case of the main sequence. If we produce, for example, of a red giant, a kind of diagram like this, like putting the period spaces of the peaks towards the larger separation, we can distinguish very well between stars which are still burning hydrogen and stars that are in the helium burning phase, and even with a different mass, so secondary clump. Here is even more precise as we got more data and we put all together. So this is an indicator that this use of the astroseismology is very powerful, especially for the use of the red giant. In the case, for example, of a cluster, if we find some red giant, like in these clusters, then we can fix the age of this cluster. And this can be even used to constrain, for example, the mass loss. Here is this publication by Milho in 2012 using the inference of the mass of red giant in this cluster, and to observe a variation of mass loss along the evolution. So this is something that actually could be very interesting to do if we observe more clusters, because by now we have only 4 clusters that have been observed. And better to go through the age dating of each part of the Milky Way. So there is this paper, for example, for the new Indy, in which we have found oscillation, and it has been possible to find the age and to understand that it is originally from the thick disk, I remember, and it has been actually heated up by the Enceladus merging. So we can go really in detail of things that has happened not only inside the star, but even inside our galaxy. I want to go through very quickly the rotation, because this is one of the other problems in stellar physics. Due to the rotation, the internal rotation, this has been already observed in the Sun. The frequencies are split in different components, and we can use these components to infer the internal rotation in very easy way. So this, for example, was the first paper observed thanks to Kepler, and we see a real indication of the rotation in the core and in the surface. But mainly it has been done, this exercise, for several stars, and to produce and to reproduce the behavior of the variation of the rotation as the star evolves, which means to understand how the angular momentum varies along the evolution. This, for example, is the inversion for this red giant. Is one of the I think that the best red giant observed by Kepler, in which we have 22, I think, the rotational splittings. And if we look inside, we can even see a difference in this layer, which corresponds exactly at the layer between the core and the hydrogen burning shell. At the moment, there is an effort to produce a dynamo model which can fit with this rotational behavior to explain if this is really the feature in which the layers in which the tachocline and the dynamo is located, the same that happens actually in the sun. The model prediction is completely different, because we say a difference of 6 times between the core and the surface, and this is not what the models predict at the moment. There are several different models, I know, probably some of you are aware, and actually each of your models can reproduce that rotation by changing the parameters, but this is not enough, because we want to know why it's in that way, why it's losing that angular momentum, and where it's going, and what is extracting. There are several ideas, like internal gravity waves, for example, meridional circulation. No one of these actually is very well explaining this loss of rotation. For the magnetic activity, if we look at the frequency, we can reconstruct. We have seen this behavior, so the variation of the frequency due to the magnetic field. But by looking at ensemble asteroseismology, so looking at several stars, like 2,576 stars, here we see that there are stars in which we have oscillation, and stars and we don't detect oscillation. And we don't know why, actually, we didn't know. If we get an indicator of magnetic activity, something that is called the S index, photospheric index, we can actually understand that there are stars which, due to the magnetic activity, do not show oscillation at all. The variation is like this. So as you go with magnetic activity up, then you don't see oscillation. So the oscillation are seen only here in the red, are the red points. On the other direction, there is actually the rotation. So as the rotation increase, which means a small period, and as the magnetic field increase, then there is less probability to observe oscillation. And also these models have been produced to see how the oscillation can be damped. For example, this is one GJH 504. Is one of these stars, is a G-type star, so we should observe oscillation. We have observed once, we observed 2. I obtained the time again 3 times, but actually there are no oscillation where we have thought to observe. And if we study the period and the rotation, this is a fast rotator. And the period of the cycle of the magnetic activity, it's 12 years, which is not too bad. It's like the sun. but it is a fast rotator. So probably there is a suppression which might be due to the magnetic activity or to the rotation. Certainly here in the Long-Scargol diagram, you see that there are also other minor cycles. And there is this model that is very interesting by Basile and Mattis for a stochastic excitation with a magnetic field, which can describe these things. I finish with the last word in which we have been involved, but is using astroseismology also to study the star-planet interaction, again with the GJ504. And to see if the model can reproduce. This is a model by coupling the best evolutionary track, so the one that reproduce observation luminosity, effective temperature, metal abundances, and we couple this model with the SPI, stellar planet interaction modeling. It's a model that has been developed by Camilla Pezzotti, and what you see is actually that she considered two scenarios in the case of star with a close companion, with a planet or no companion. And the two scenarios are the solid and the solid is no engulfment, and the dashed line is with the engulfment. So probably this is the best indication. So the high rotation of this star is due to the engulfment of a planet of some Jupiter mass in an epoch that is very recent. So this engulfment has produced this high rotation, which is not really expected for this age of the age of this star. And the same has been here in the third panel. You see the X luminosity and the modeled with the observed by Rosita. The magnetic field, sorry, I just give this. The magnetic field produces also splittings, and it has been observed. So now we are able also to measure the magnetic internal field through the splittings. So when there is a rotational splitting is symmetric, when it's not asymmetric, it is due to the magnetic field. And we have several more stars in which the magnetic field has been already observed with field from 10 to 600 kilohertz. And so there is a lot of things going on. I want to finish only with this, sorry, which are the next step, of course, observing more stars. We know that actually PLATO is going to observe a main sequence stars, but there is also the possibility of subgiant, red giant as complementary science. So there will be other kind of science that can be done also with PLATO. And a lot of expectation there is also with the new submission of the proposal for IDIN, for going to see in the bulge of the Milky Way and possibly in dense field to study the evolution of clusters. And sorry for taking a longer time. I finish here.
So questions? He is working on the project.
Ah, very good. And everything works well? Like you.
I have a question about the giant. So mixed mode allow, if I understand, allow very precise determination of the parameters, in particular the mass, no?
In particular, the age, I would say, but for
the age, how the age? Because I understand.
because these modes, which are the mixed modes, are actually probing really the interior, the core. So they give information about how much fuel is still in the core. In the red giant. Well, whatever it is, that if there is helium, if there is, well, you have to think that it's like an instrument. Let's see, there is this, yes, with the mixer mode like this. So this is the wave of the modes that you observe, because many they are one modes. They are mixed in the sense that they behave like P modes, so concentrated in the interior, so really probing the core. So up to 0.01, and the core is very small actually in this.
We know that the core is image essentially.
Yes.
So
well, but then you know how deep it is, and also the shell. If you have the hydrogen shell. That's interesting. Yes.
The interface between the core and the envelope.
Exactly.
The shell is located.
Yes. I don't have the shape of the.
So my question is how you can get the image from observation. I understand that you can get the mass, and then from the mass.
No, you get it from the model. No, you have to model. Of course, you don't have something in the red. Okay, you have you can have, but it's with an error from the delta P, from the difference in between the period spacing of the gravity. You have an hint. And that is already a demonstration, yes, giving of the age, so in the phase, let's say. So since you know in the evolution, they are in a phase, if we want to plot like a HR diagram, they are all there. No, the stars.
So in any case,
no, but the delta P actually give you the difference in period, give you a precise. Oh, well, this. Sorry for this. Very quick. Yeah. So let's say that if you measure the peaks and you see a difference of 200, you already know that is burning helium and not hydrogen. Well, red giant, you mean this one. Among these, if you want to distinguish, yes. If you want to distinguish, well, the main factor was to distinguish because they are all there actually. If you want to plot these, they are all in the same luminosity, temperature region, but each of them according to the mass that you don't know, and according to the feature in the inside, has actually a period which make them very different. Then, of course, if you want to know with a great accuracy the age, you have to go through model. The best thing will be to use everything.
No, because in principle, if you know the mass of the red giant, you know also the age from a stellar models. But
yeah, but that is not.
This is
yeah.
model dependent.
Yes, that is model dependent, but it's not enough. Yes, but that is not enough because still you don't know, you cannot distinguish exactly from one that is exactly in helium burning phase from one that is already still burning the hydrogen in the shell, let's say. It's still, it's something more precise. Just by eye, you can put everything together and just to know that this is a red giant or a clump or a secondary clump. That's age in this sense. Then, of course, if you want the number and precise, then you have to. Yeah. Then you have to use. Yes. Then you have to go through the model. Yes.
Il ricordo il nostro proprio non solo come stars,
in my view.
No, but you can ask also other
Okay.
things. If I don't know, I will say I don't know.
You mentioned that one of the things also uncertainty is previous 1B, preview of the surface, and there's a number of works on the characterization of retroelectric gels, for example, the definitely burning state.
Exactly, yes.
So, for that, PLATO Joy say, okay, definitely will be burning, but when just if you look at it, it's highly asymmetric.
No, it's not.
Surface
It's a problem.
giant
Yes.
comments. How big are they in that case? How confident we can say that's the planning stage?
No,
They sound very confident.
no, it's still a mess. In fact,
Okay.
it's not. I saw, yes, it's a 3D modeling which are working on that, and so the effort is to try to put this little bit of 3D model, because to do everything in 3D is not possible by now. So what they do is try to link. We're trying to do this kind of game to link these 3D models of the surface to the 1D model of the inside, using the gamma 1, for example, using only something of this profile. I don't know. Well, I had a poster on that. Still, it's not something that you can. No. Yes, in principle, it's what you do. It's still not.
No, because they sort of really they did the best they could. I mean, the paper is quite, the technology is quite solid, quite clear. They try to put all the
No, but this is what there is a lot of effort.
When you showed how what weeks or weeks is a big source, and that starts really strongly, you see the popcorn interferometry, not symmetric at all. And the surface is highly turbulent, highly dynamic. And so I was wondering, okay, but so how strong are the results? That's yeah, that's the best we can do.
Yes, for the moment, I think that is the best. I see that they are working on that. I'm not satisfied in the sense that it's not something that you can use in your thing, but this is what they are doing, and it's the. I think that is the right direction. I would say. I don't think that there are other ideas. I don't see other ideas around. That's the problem, actually.
Yeah, it's something when you mentioning magnetic field. What do you mean?
Yeah, sorry, I went very quickly. Yes, I mean the magnetic cycle, because these are solar-like stars, so they have two things, okay? So there is the magnetic activity, which is similar to that of the sun, with periodic cycle. And like many of these stars has been able to observe through S index or calcium 2 HK indicators, a periodicity of a cycle. These cycles of its present, and again give you some hint on the phase of the evolution of these stars. You know, if it's Fagle or if it's a sunspot. So what you expect usually is if there are a long period, then it's like it is more evolved. If it's a small period, then it's very active. So this is something, and you can observe this effect on the frequencies, or you can try to relate it to the age and to the phase of the evolution of the star. Then there is another thing that is to study the presence of the magnetic field inside the star, and this has been done only for some, okay, 50 stars, not many. So first of all, it has been done a kind of theoretical approach. So to see if there is a colloidal, of course, you use a simple approach, simple magnetic field. A colloidal field can have an effect on the oscillation. So the model is include what we know. So the Reynolds stress plus the magnetic stress, let's say, the rotation stress, and all the effects. And then you can disentangle and to see the effect on the oscillation. So actually there have been the possibility to observe this splitting. The splitting is just like a Zeeman effect. So you don't see a very nice peak, you see a splitted peak. This is something that you observe also in the instrument. If you see an instrument and make to play the string with magnetic field, then you see the effect of the string, of the splitting of the frequency. What is nice is that according to if this magnetic field is poloidal or equatorial or well, it has not been tried with very sophisticated magnetic fields, but this makes an effect that is different than the rotation because produce a non-symmetric effect on the frequency that we observe. So this is very interesting. And it has been done from the theoretical point of view for several years. So what is nice is that this is a theory-driven result. Then when you went to observe better in the stars that you can identify and you can observe for longer time, because one of the problems of these stars for the oscillation is that you have to observe for a long time because the oscillations are stochastic, so you don't see them all the time. You observe and to collect data for a long time to see all the data. Then we really identified this splitting and non-asymmetric splitting. And so there is all kind of modeling that now has been started just because this is something new, 2021, it was the theory, 2024, it has been found the observation, which need to be better. And this is together to what actually we were thinking, and this observed that there are some stars that should show oscillation and actually not show oscillation. And this is due to probably a suppression of the magnetic field and probably rotation, surface, of course, rotation on the surface magnetic field. We are not speaking about the inside in this case. Because what we think is that there is an effect of energy that is taken out by the oscillation from the observation, so they don't get out, let's say. Okay, very simple way, because it's a matter of a balance of energy. So how much the convection give energy to a mode, how much is taken from the rotation and the magnetic field. This is, and is everything balance. So yes, there is time for more modeling and to understand better these things. Let's hope.
The last question. My memory could be lost where I look at that. As you know,
Asteroseismology.
There is a third type of oscillations, which is so-called F modes.
Yeah,
I don't know if you spoke about them.
No, actually, but I think that I've shown actually.
They are detected.
No, in the other stars has not been observed, but in principle they should be. Yeah, here gravity, surface, wet dwarf. Okay, so in wet dwarf probably they have been observed. Still the F mode are seen in the sun. Well, in the sun, you know, you can observe better, yes, in the sun, at the surface.
Associated.
No, but you see, there are actually different. I couldn't go. I tried to be able to give a presentation that was kind of interesting or approachable by everybody. I don't know. But of course, there are a lot of efforts also for other kind of stars, like the Prime sequence, the M dwarf, Delta Scuti, in which we have seen also solar-like stars, even Delta Scuti. So all the stars actually are not so easy, and they present only that kind of modes. In true, you can observe in that big power spectrum, there is space for a different kind of behavior and excess of power due to different things. So by now, yes, yes, what I see is that actually in the wet dwarf they have been observed, but the wet dwarf is one of the other stars in which several tools have been already developed before, like for example the inversion for the rotation or for the density of the core, a lot before that we could observe. But in the gravity, in the wet dwarf, we have the gravity waves. So it was a bit different. Yeah.
We can flex again. Give you a couple of weeks with the next seminar by Kepler, right?
Sì, ma ti volevo chiedere una cosa,